What you are looking at right now is a spectragram of my voice, as I'm speaking into a microphone. When I first saw this, I was quite perplexed by all the strange shapes and features embedded within the image. It made me wonder, just how is speech analysis done? Could this be how smart speakers do speech to text? Take a minute, pause and ponder, just how does all this stuff around us work? The first thing I always like to do when starting a new project is to play around with it. For example, if I make the E sound, it makes one shape. And if I make the A sound, it makes a different shape. What this might tell you is that all the different sounds that we make when we speak are composed of different frequencies. Maybe we could characterize all the different shapes and features of the spectrogram image to identify the speech and turn it into text. Now, that sounds easy enough for you and I to do, but telling the computer to do it is a much more difficult task, especially in real time. I was so intrigued by this that I set out to build my own speech analyzer, and I wanted to take you, my dear viewer, on the journey, or tour, of all the interesting math that goes into speech analysis that I learned along the way. The first thing I want you to ask yourself is, how do we classify these sounds? There's a fantastic mathematical tool called the inner product that provides the mathematical framework to do just that, which generalizes the notion of the dot product for vectors, but for sounds. What this means is that any intuition we can build up for the dot product also will apply for the inner product. Note, this is just one way to define the inner product, and there's many ways to do so. It's important to take time to build up intuition. If we dot product two vectors together, the result shows us how similar the vectors are. For example, take v equal to 3, 4, and dot it onto x, 1, 0, to get a value of 3. We do the same thing for the y vector, and get a value of 4. We get the vector is composed of 3 parts x, 4 parts y. You can do this dot product with any vectors, but these vectors have a very special linearly independent property and are also basis vectors, which means that you can both deconstruct the vector into how much it is like them and reconstruct the vector from them. Plotting this onto an xy plane and projecting this vector v onto each of these vectors, we get some geometric intuition on what the dot product is doing. Another example, w equaling 2, 4, projecting the w vector onto v, we see by this dark blue line how much of v is composed of w. This projected length is the dot product, but scaled by the lengths of the vectors. For x and y, the length was 1, and the projection was just the dot product. If we move the w vector around, we get some strange changes of the projection, and this can kind of build up our intuition here. Let's add a red line to indicate the value of just the dot product, non-scaled, and we can see what the dot product is telling us as we move w around. We see that the value is biggest when the vectors are aligned, or most similar, and smallest when they are at right angles. It's 0, in fact, when there's nothing in common. As we move further, the value becomes negative until we get the exact opposite value for the vector. And then if we keep moving the vector, we get another point where the vector dot product is 0, and the vectors have nothing in common. So, what if instead of doing this with vectors, or points on a grid, we could do it with sounds, deconstructing the sound into what letters make it up. For example, we could take the phrase I am, and deconstruct it into I, a, and am sounds. This is what the inner product does for us by generalizing the dot product. It says, so long as our vectors obey these properties, then we get a dot product-like operator called the inner product, where our intuition carries over from regular vectors to these sound vectors. Now, to not bog down the video with too much of the ocean of math behind this, and just focusing on building up the intuition, I've left links in the description to proofs on my website, explaining this in greater detail. The inner product for functions where our sound vectors is defined as follows. If we take the inner product of two sound vectors, we'll get a value, 0.75 for example, that we can quantify as to how similar they are, just like the dot product. You can see the intuition behind this if we look at the integral in the limit form, where the time sampled for each of the sounds corresponds to the index of the dot product. This is how the sound inner product is computed numerically for a large number of samples n, with the fast sampling rate delta t. Interproducting am with the A sound yields the number 0.72, and if we interproduct the am sound with the M sound, this yields the number 0.28. We see that we can deconstruct the am sound into its parts. Let's build up some intuition relating this back to the dot product. We see that the value is biggest when the vectors are aligned. This must be the A sound. Smallest when they are at right angles or zero, nothing in common. For example, the I sound would have nothing in common with the A sound, ideally, and negative if it's in the same but exact opposite direction. This is what you would add for noise cancelling. And then we have another vector that has nothing in common with this vector. Ideally, this would be the M sound, as an example. Now, we could do this with a bunch of different sounds, characterize them, and build up a dictionary or catalog of all the sounds, right? There are just 26 different letters in the English alphabet, and we could have a bunch of different sounds that make them up. Maybe we could build up a simple classifier for all these different sounds, and that would be great, except there are a bunch of problems here. The first problem is that this relies on how long the sounds last for. For example, A and A are two different sounds. Also, the only reason that the deconstruction worked is because we are multiplying by 0, forcing these sounds to not be similar to each other. If we interproduct them together without these zeros, then this no longer works. The second problem is that there's no guarantee on previously knowing where these sounds will occur. We need a way to move the sound around to indicate when the sound is happening. The third problem is letters don't exactly correspond directly to sounds. For example, A can be the sound in cat or father or arise, and that sound could be even different depending on the environment. All of these are different A sounds. Let's just do a quick experiment to test this out. You might get the false impression like I did, which is that if we were to just identify the frequencies of each type of sound for letters in the alphabet, then we could do speech to text. What I thought going into this project is that if I identify the frequencies of the Y sound, for example, that I convert that into text. However, it changes with the pitch of my voice. Y. Notice that it moves the line higher, the frequencies of the E sound change. Let's try a different sound. A. Thus, we can discern these sounds aren't just composed of specific frequencies. There is a certain characteristic spacing to each one of them. Unfortunately, as we have just shown, in order to classify even just the A sound, we would need a whole spectrum of different A sounds to identify it in the speech. Again, letters don't correspond directly to sounds. For example, A can be different sounds in cat and arise. And the environment that the sound is in affects it too. So let's start off with something much simpler. A single tone or frequency, a sine or a cosine wave. And the question is, how much is the sound similar to a single tone? How can we represent the sound in terms of all these sines and cosines that we understand really well? This is often what you want to do from a representation theory perspective, which is finding the representation that makes the most intuitive sense for your data. For intuition, this is what a single tone looks like, and we see that there is a single line on the spectragram. If we take 3 tones added together, play them, we get 3 lines on the spectragram. Interproducting this sound on a bunch of tones is the essence of the Fourier transform, which tells us what tones this sound, S of t, is constructed from. For example, the signal I used for the tone is S of t equals 1/2 sine t plus 1/3 cosine 3t plus 2/3 cosine 5t. And if we inner product it with a tone, we see that we get 1/3 for the third frequency. We get 2/3 for 5. And we get 0 for 1 when there's sine. And this is because we use cosine. If we use sine here, we get 1/2. The reason this happens is because if you inner product sine and cosine together over at least one period, you get 0. In fact, you get this for any two cosine tones with different frequencies. And if they are the same frequency, then you get pi. If we normalize this, you get 1. Thus, we have two types of tones that we can deconstruct our sounds into that also happen to form an orthonormal basis, which means that we get that nice deconstruction and reconstruction property, where the coefficients are these inner product projections themselves that tell us how much the sound is like each frequency. This is often simplified using complex numbers to get a different representation, the complex exponential. The complex exponential is a circle in the complex plane, and how fast we go around the circle in a single second determines the frequency. This is just another representation of a single tone, and the Fourier series is the addition of a bunch of tones represented by these circles of varying frequency. And if we add up all these tones, we get our sound back. Similarly, we can see that our sound is composed of these individual tones. The Fourier transform says that this sound can be deconstructed into 3 tones or circles, and the inner product of the rest of them results with 0. These coefficients, or more specifically their amplitudes, is what you see in the spectragram. The phase information is also important, as we'll see later, but it's usually not represented in the spectragram. By the way, there's an alternative form for the Fourier series using a different trig identity, and you see that the complex amplitude and phase line up with these parts of the deconstruction right here. Plotting the amplitudes of the Fourier series coefficients, we get a graph. This is called the power spectral density. If we take a bucket of sound every 20 milliseconds and color the amplitudes of the Fourier transform, we get the spectrogram that we've been looking at this whole video. We now know how to deconstruct a sampling of sound data into frequencies. How do we know that this sound happened here? Fourier analysis works by assuming these sounds repeat forever. What if the sound just appeared for a little bit? You could try bucketing the data and performing the Fourier transform on each bucket. You would know that for this section of time, these tones occurred somewhere in that time interval. Another method is to use an indicator function that tells us when the sound is occurring as we move it around. For this example, I'm going to use the bell curve, and wherever the bell curve is moved to in time, it will tell us what occurred in the window. To move this indicator function around, we attach a shifting parameter to it, tau. What this is the convolution integral, where you are moving a window and seeing exactly where the function you want to relate this window to matches up with the window. The convolution integral as a moving inner product is a moving detector, or a classifier that tells you at what point in time for our sound case that we are trying to detect with an inner product occurred. Now here's a question to ponder. Why pick this specific bell curve? We could make the bell curve less spread out, larger in amplitude, or we could have picked a different window function altogether. You see that by changing the support that the bell curve isn't nearly 0 over, we get a different resolution in our result curve above for when things happened. More specifically, the narrower the bell curve is, the better our time resolution gets. You could pick many different types of window functions as your detector function, and if they satisfy a certain set of properties, they're considered wavelets. Now, wavelets are a type of transform with similar properties to the Fourier transform, and the study of wavelets can be used for analyzing and characterizing signals like the sounds we're making in many more ways than just frequency. For example, the Gabor transform is a part of a special class of wavelets called short-time windowed Fourier transforms. And if we multiply our bell curve detector function with our sine and cosine tone detector, the Fourier transform, we can now detect within a range at what time these frequencies occurred at any given point in time. One of the nice things about this bell curve is that it gives more weight to what occurred at its center, let's call that tau, and gives less weight to what happened further away from tau. Putting these two ideas together, the Gabor transform allows us to better tackle time-frequency resolution. The time-frequency resolution can be controlled by changing how spread out the bell curve part of the Gabor transform is. Let's take a look at a demo to see what exactly that means. You can see as I'm recording this that we've got pretty good time resolution because we've lowered the number on our Gabor transform up here. And this tells us exactly at what points in time speech is occurring. But by increasing this, I get better frequency resolution and can start to pick up what frequencies make up the sounds that I'm making. And the best practice is to try and find somewhere in the middle where you can identify at what time and at what frequency the sounds are occurring at. In the book I've been referencing throughout this project, A Wavelet Tour of Signal Processing by Stephen Mallet, they give a nice figure for time frequency uncertainty. These are called Heisenberg uncertainty boxes. The figure shows that while maintaining a constant area, you can choose more time or more frequency resolution, but not both. Together you get a lower limit to what your resolution can be dictated by these equations. You have to make a trade-off between more time or more frequency resolution. You can see here that there's a distinct impulse that happens here, but as we increase the frequency resolution, we lose certainty at what point in time that impulse occurred, and gain more resolution information about the frequencies that were part of the signal. It's finally time to talk about formants. Now that we have an idea of what's going on in the spectragram and how to interpret what we were looking at with the Gabor transform. Unfortunately, at this point in the video, I've realized that the screen recorder I'm using is affecting my real-time demos, and I'm going to have to solve that problem later. However, I've grabbed a screenshot of the demo instead. You can see that I've made a bunch of sounds that all have some distinct lines in common. The first is me saying something, and it's made up of a bunch of lines. The second is oo, then e, then at a higher pitch. Now, each of these different sounds seems to have the same type of lines corresponding to them. Turns out, there's actually a name for those lines, where I've highlighted in green, that linguists call formants. If we go to the IPAchart.com, we see that each of these sounds corresponds to a specific position of your tongue in your mouth. I highly recommend you pause the video, go to IPAchart.com, and try this out. It's very enlightening. For example, if you put your tongue at the top front of your mouth, you get the E sound. More interestingly, if we correlate the frequency that the first and second formant happen at for each sound, we get what is called a formant plot that looks very similar to the IPA chart. Thus, we can roughly determine what type of sounds someone is making from these formants. For example, for the male voice, these are where we could expect to see the first and second formants typically. Now, this isn't the same for everyone. There's some variation to this. Say someone makes a sound, then we can track where it lands on the formant plot and determine the closest symbol that it is to. This is the magnitude vector error method, and it offers a way to classify what sounds the person made from the formants in their speech. So, in order to identify what points in the spectrogram belong to the formants, we have to do something called ridge detection. If you look at the spectrogram with the amplitude as a height rather than color, you'll see that the formants look like ridges. Keep in mind that while yes, you and I can easily see where these formants are occurring, the computer needs a set of rules to determine where these points are. These rules act as the computer's eyes. These formants are locally where the value of the spectrogram is at a local maximum. In calculus, you may recall taking the derivative and setting it equal to 0 to find all the maxes and mins for a given function. It turns out that the Gabor transform has this very special property for these ridges. If the derivative of the phase equals the frequency, then this is where the ridges will occur at. There's a proof in the link in the description. Let's unpack this for intuition now. Phi is the instantaneous phase of our signal. For example, you can have a modulated tone that looks like this, which is used for FM, AM, and PM radio communication. As a simplified example, consider the instantaneous phase to be a single frequency times time. Taking the partial derivative of the phase with respect to time, we get this expression, which looks pretty familiar, right? What does this mean, though, for our Gabor transform? The result of the Gabor transform is a complex number for each frequency omega and timestamp tau, which we can break up into an amplitude and a phase, like this. You see that we have this very nice similarity here, and if we take the partial derivative of the phase part with respect to tau, we get the instantaneous frequency. Now, only if this equals the frequency of our Gabor transform at the point it's at do we get a ridge point. We can make this a rule to check for all the points in the spectragram. Now, approximating the derivative, we should get approximately 0. However, to what error? So, the absolute value of this expression must be less than that error. And for some delta, there exists an epsilon such that this must be true if the limit exists, which it does for the majority of speech you would be analyzing. Thank you, real analysis. The delta here is our sampling rate, and this equation is exactly what I coded in for ridge detection. If a point in the Gabor transform satisfies this rule, then I simply colored it green, yielding a list of ridge points that make up the formants. And I was quite happy to see an application for an epsilon delta proof come up in this project. Now, getting the formant plot working and identifying what points belong to which ridges or formants, I'm still working on at the time of recording this video, and will most likely be in a part 2. The tools for identifying what points belong to which formants I believe will take some point set topology, which gives us the framework for what points are connected together. I hope this video gave you some intuition behind how speech analysis is done, and some of the math behind it. This only scratches the very tip of the iceberg, especially on how linguists analyze speech with spectrograms. I'm planning on making the software I created on this project available to you to test this stuff out for yourself once the bugs have all been worked out, and it's at a good release point. I'm really curious to hear everyone's questions in the comments. And if you would like to support me and the production of this tool, I've got a Patreon link in the description that you can donate to. This video is also part of the Summer of Math Exposition 2 that Threeble and Brown is putting on. I encourage you to search YouTube for the other submissions in the Sum 2, as well as Sum 1. There are hundreds of great videos and blog posts with mountains of interesting information to learn. See you in the next video.